Okay, so in the previous class we had the frequency response for the first order system of tau s plus 1, and we saw tau is 1 for teaching purposes. And what we did, we replaced s with what it is, I omega or j omega plus 1, and we had the 2 log in the base of 10 of 1 plus 1 plus omega square, and we plotted the amplitude part of the body diagram. That's right, so here is omega. We started from 0, so 10 to the power of 0 is 1 in the log scale, 10 to the power of 2, and 10 to the power of 3. And we saw that this is a low pass filter. It comes here with some certain frequency and goes down. So you saw that this value, if you notice, was minus 3, and this value was how much? Minus 20, and this value was minus 40, right? So this is, if it's number A, I'm plotting A versus omega, we're changing omega. So the name of this frequency when your system low pass filter works, this frequency is cutoff frequency. Cutoff frequency. For example, for this system, cutoff frequency is 1 radian per second. So omega is radian per second. That's right, excitation frequency for the first order system I'm talking about. Obviously, if you select tau 2, you're going to have different cutoff frequency. That's right. For example, if tau is 2, before going to this is the low pass filter, as I told you, low pass filter, and filter out the higher frequency. Filter out the higher frequency. Only accept the low frequency. You see here. What does it mean physically? It means that if you have the RC circuit as the first order system, V in RC and VC, and we found VC over V in, we did together, that's right, in MATLAB and mathematics, was again tau s plus 1, remember? And the tau of this first order system was RC, resistor and capacitor. It means that if you apply harmonic input to the system, your V in is the AC current, means sine omega t. This is sine omega t, means AC current, that's right, DC current, AC current. So for the low value of the frequency, VC gonna be equal to Vm, because log of the 1 is 0. But if you increase, saying that tau is 1, like this case, tau is 1. But for higher frequency, the amplitude of the VC is decreasing. Amplitude, respect to the V in. I'm gonna plot it in MATLAB and Simulink today. See what I'm saying, everybody? So now let us stick to, for example, tau is equal to 2, not 1. So x over y becomes 1 over 2s plus 1, right? So it's better that we write like this. So it's going to, your A gonna be 20 log of, again, it's gonna be 1 over 2I omega plus 1. It's gonna be 4 omega square plus 1. The amplitude of this, when you increase the time constant for the first order systems. Yes? Understand? So if you, how much is the cutoff frequency for this system? Guess it, guys. How much is the cutoff frequency for this system? Can you find it? Cutoff frequency that was giving the A-3 here was 1. Cutoff the frequency C was 1 radian per second. What about this? Any answer?
2.
How much? 2. Okay. Use your calculator, guys. Double check. Exactly. So let us try it. So it's gonna be 2 log 1 over, he says, cutoff frequency gonna be 1 over 2. That's right? You mean this, that's right? Half. So it's gonna be 4 multiplied by 1 over 4 plus 1. Can you calculate this, please? Let me know the answer. Obviously, this is 1. This is 1. Exactly. So you see that by increasing the time constant of the first order system, if I want to plot, I'm changing the color, okay? Let me finish this. So the cutoff frequency by increasing the time constant decreases to here. Omega is half. Here was 1. So you're going to have this. See what I'm saying? So now you can judge. See, I increase the time constant. If I say tau is 3, what is the cutoff frequency? Give me the answer. So if this is omega is 3, so your x over y becomes 1 over 9 omega square I plus 1. Right? So as your friend says, it's going to be 1 over 3. To make this ratio, this part 1. That's right. Everyone understand this? So when I say, if I increase this, you're going to have this 1 over 3. Here we go. So this way, you are going, you mean tau is increasing for the first order system I'm talking about. On the other hand, if I go to the physical example, if you increase the RC resistor and the capacitor product, you're gonna make your cutoff frequency lower value. You are filtering out lots of the frequencies. See, for this case, you are filtering out lots of frequencies, and you have very, very low pass filter. This means low passing frequency filter. Only low frequencies you have the same value for this. Everybody understand? Yes? Yes, everybody? Can I go to the next page for the phase angle? Can I go? Okay. So let us stick to our original problem. 1 over I omega plus 1, the first order system. Based on whatever I taught you, the phase angle of this x over y phase angle is phase angle of the numerator, as I taught you in the previous class, minus phase angle of the denominator, I omega plus 1. Remember, I taught in the previous class. But number 1 from the high school, I'm not getting help from high school, is 0I plus 1. That's right. I omega plus 1. Based on whatever I taught you, got here in the previous class. Remember I taught you in the previous class? Imaginary, this is number 1, real number 1. Here we go. What's the angle of this based on the unit circle? Remember unit circle in trigonometry? Do you remember it? Oh man. Unit circle here is 0. Here is pi over 2. Here is pi, 3 pi over 2. Here is 2 pi. But it's here. It's here. It's 0, that's right. Why is 0? Because I taught you in the previous class, if you have a complex number like this, the phi tangent of the phi equals to, from trigonometry, imaginary part over real part. That's right. Yes? What's the imaginary part of this? 0. Which angle of gives you the angle 0? So it is 0. Here we go. Angle 0. Because this is here. Number 1. Understand what I'm talking about? Yes? Stop me if you don't. Now let us go for this. Minus, as I told you, tangent inverse of imaginary part over real part. Here we go. Imaginary part over real part. Understand everyone? Yes? So what I'm gonna do, let me plot this omega A. This is radian per second. And now I'm plotting as MATLAB does. I'm going to do that today to you. Omega radian per second. Here is 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. It goes away. Let me see. Yeah. Okay, so see. Exactly MATLAB does like this. Okay. Here is phi, phase angle, and this amplitude. So we plotted amplitude for this specific problem where the tau was 1, was like this. This is low pass filter. And we have found the cutoff frequency, C cutoff for this was 1 radian per second. Okay. Now, let us change the omega. When the omega is 0, the phase angle of x over y is 0 minus 0, because tangent of 0 is 0. It's here. Here we go. Understand? Now let me change the omega to 10 to the power of 0, which is 1. So the phase angle gonna be 0 minus tangent inverse of 1 divided by 1 is 1. Which angle is which angle gives you 1? Which tangent from trigonometry? Come on. Tangent of which angle is 1? Yeah, 45. So it's gonna be minus 45 degree. So if I say here it is, say, minus 45, and here minus 90. So it says at 1 here we go. If I say omega is, I don't know, 10 to the power of 2 or 100, so the phase angle is gonna be 0 minus tangent inverse of 100. Can you calculate for me? Which angle gives you 100? Or let me go even bigger. Yeah, 100. It is almost 90. That's right, from trigonometry. Gonna be minus 90. Here we go. So this is gonna be the phase angle of the body plot, starting from 0 and 90. Now let me visualize this for you. Before going that to the MATLAB, okay? You see that, guys, here the slope of this line increases, has a slope, that's right? Slope, that's right? Increases for almost, see, from here to here. 20 decibel, because the scale of is the decibel, like as the sound, okay? Decibel over decade, because this is, see, 10. So the slope of this minus 20 decibel per decade. So decade is every 10, that's right? Decade, how we define. But this downward is minus 20, see? 20, almost 20. Okay, decibel over decade. I just want to let you know. Then I'm going to visualize that when I say physically, this low pass filter and this, what does it mean in reality? This phase. Can I go to MATLAB? Yes? Okay. So, if I go to MATLAB, and plot encoding and the Simulink, and I want to plot for the first order system. Let me freeze this. Okay, guys. So what I'm gonna do, first I want to develop MATLAB code. So I'm gonna say num, let me CLC clear all, close all. I'm gonna share with you. Is the first order system num is 0 and 1, and then 1. First time constant, and it's gonna be 1 and 1. Then 2 is gonna be time constant 2 and 1. Okay, and then 3, it was 3 and 1, as we did exactly. So I'm gonna say figure 1. Okay, figure 1 body, it has a command num and then, here we go, that's it, and grid. Okay, first let me run this. Body coding. Okay, and if I do it, you see that, oh, then 1. Then 1. Okay. Here we go. As you can see here, 1 is the cutoff frequency. So the value is minus 3 decibel. Phase 0 to 90 as we plotted. See here? At the cutoff frequency of the 1 for this problem. Now you can say, okay, I increased that, so hold on. Body, then 2, and hold on. Body, then 3. Because I increased the time constant, see? See here? So if I plot as we did together, you are you're filtering out, as you see here. See, this is the blue line is for the time constant of the 1. Here's the for the red one is the time constant of the 2, and this is for the time constant of the 3. See here. See here. Okay. So the cutoff for the frequency was here 0.1, 0.2, 0.5. See half. Okay. See what I'm saying? Yes. And actually, we can put the legend hopefully. Hold on, just yes. Let me tau equals to 1. Okay, here we go. As you see here, the blue is for time constant of 1, red one is time constant of 2, and okay. Cut off the frequency, as your friend asked. What is that? Okay. Look at here, guys. This is the magnitude of closed loop transfer function. Yes or no? What was your name, sir? Christian. It is the magnitude. So closed loop transfer function. So in the cutoff the frequency, that's right. At cutoff frequency, this is the frequency that your filter wants to leave that one value, this one value, because logarithm of the 1 is 0, that's right. Remember, logarithm of the 1, log of the 1 is 0, that's right. So here is 0, that's right. Means that your output exactly magnitude wise is equal to input. See what I'm saying? Remember? So when this is 1, okay, means that at omega 0, this is 1, that's right. Logarithm of 1 is 0. So for low frequency, this is 0. Means output over input. But we have a frequency that here was how much? 1. That's right. Here was 1. That this curve is gonna leave that 0. This curve gonna leave that 0. Means your output gonna decrease amplitude wise respect to the input. See what I'm saying? And that's why we name it the low pass filter, because it's filtering out the decreasing amplitude on the other hand. Yes, exactly. Yeah, exactly. So again, this is for the first order system. When I cover the second order system, I'm gonna cover it. Okay. So, but I want to visualize through Simulink. Okay. Through Simulink. How? I'm gonna make a. Let me open step ramp response to save time. I'm gonna share this with you. There we go. I want to visualize these graphs both together, okay, for the low pass filter. Okay. Okay. I'm gonna copy all of these to new. Simulink file, move all of them here. Okay, first I'm gonna change, because it's the first order system, that's right, time constant of the 1. We have to put the open loop transfer function, remember, in the Simulink. But here I have to remove input as the RAM and put what? You tell me. Put what? Sine. Yeah, exactly. Okay. So sine. Oh, sine wave. Here we go. But why is sine wave like this? Oh, sine wave. Here we go. So I'm gonna put sine wave here. Here we go. And I just want to first cut it from here because I don't want to plot it yet. Okay, so I'm gonna double click on sine wave. Amplitude is 1, and the frequency I'm gonna put as 0.5. Okay, remember guys, let me see, let me show you. Okay, at cutoff frequency was 1 radian per second, remember? I'm gonna put at 0.5 here, lower than frequency, cutoff frequency, even 0.3. Let me put that. Here we go. See what I'm saying? So, and now I'm running that for 10 seconds. Let me put that. Yeah, first let me save this as body first order system. Okay. I'm running with the frequency lower than cutoff frequency. If that's the case, oh, this is much, I need more than that. Say 50, 70 seconds. Here we go. You see that almost the amplitudes, they are the same. You see that? Almost. Okay, they are the same. But they have a slight what? You tell me. They have a slight what? What, guys? They have a slight... Yeah, means... Look at here, guys. Means phase angle. Phase angle means this in mathematics. When you write in trigonometry sine omega t and sine omega t plus phi, this phi means phase angle, that's right. So you see that for 0.5 almost, you have minus 20 degree. If you revert it to the time, it's gonna show you this kind of, see, phase angle. These are phase angles, guys. See, these are the phase angles. Phase angles. See what I'm saying now? So for the low frequency, I selected 0.5. The amplitudes, they are the same. So that's why its logarithm is 0. See? 0. Now I'm going to close to what? To cutoff frequency. Let me do that. So I'm going to do it here. See here? I'm going to go to here. So what was the cutoff frequency from your notes? 1, right? Radian per second. Here we go. Now I'm gonna, again, the same system, time constant is 1. Okay. Now I'm gonna plot this with other two. Oh. Right click. Comes here. Do you see, guys? There we go. So let us see what's happening. Oops. Amplitude decreased. That's right. This red one. Do you see that? Yes? Do you see that? And the phase angle is much, much higher as we plotted. See? At 1, phase angle is almost minus 45. And it is. Or pi over 4. See? Pi over 4. The phase angle. See what I'm saying? Yes? Now, if I even increase to if I copy, I want to compare more. Move it here. Okay. Max 4. Now I go to higher frequency. Say 10 radio per second. Means here, guys. 10. Here. Higher frequencies. We passed the cutoff frequency. What do you expect to tell me before running? What do you expect to see in amplitude? Tell me. What do you see to expect in amplitude? Huh? What do you see? What do you expect to see? Anyone? Oh, disconnected? Let me close everything. Hello, disconnected? Hello? So, I increased the frequency to high frequency. 10. Here. Here, 10. What do you expect to see? What do you expect to see in amplitude? You see much, much lower amplitude. That's right? Yes? This green one. Yes? See what I'm saying? Okay. So when we change the frequency from 0 to infinity, you see that the low pass filter amplitude decreasing. So on the other hand, the output doesn't follow the input. The blue one is the input. If I increase amplitude to a large value, the output never follows that. It goes to 0, its amplitude. So that's why we say low pass filter, only passing the yellow line, only passing the what? Low frequency. The green one, high frequency, it doesn't follow. See what I'm saying? Filtering out. See what I'm saying? Yes, everybody? Good. So this is function of the low pass filter. And that's it. And this is the error signal, that's right? Error signal of, let me remove this. Error signal between the input and output. So see the error signal of this is 0.3, okay, in amplitude. But if I want to plot the error signal of this, or let me do this, for God's sake, to be visible. Yeah, sure. Your voice is very mumbling. Cannot hear you at all. You have noise. You have to use the noise filter. So yes, exactly, exactly. Yes, it is. Yes, 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 yes. Yeah, exactly. So when you're designing the audio or the visual system, so you need filters. Even that you are go to the smart TVs, that's right. You see that there are some filters. They are giving you some options. That's right. See what I'm saying? So now this is the error signal. The yellow one was for the low frequency, the error signal between the input and output. But the blue line is for the high frequency. See the error signal increases for the high frequency. So meaning that this is low pass filter. See what I'm saying, guys? Yes? Yeah. Good. So you got the real understanding of the body plot. So whatever I'm saying is valid for any first order system in this format of 1 over s plus 1. That I'm teaching in ME430 in detail. That can be spring and damper, can be RC circuit, can be the tank of the fluid. That they are giving you what? This transfer function, closed loop transfer function. Understand everyone? Hmm? So after having this, let me drive. Go back to notes, and I'm gonna share the files with you. Okay. Uh, Now, if you have this transfer function, let me tell you this. In this transfer function, the first order system that we derived everything together, you have one pole, only one pole. There's no zeros, that's right, because zeros is the roots of the numerator, poles are the zeros of the denominator. The poles of the system is in the left hand side, imaginary, real, is, as I told you, is 1 minus tau. So system is stable because it's in the left hand side. You have only one pole, okay? Now, oh my god, I have, okay, let me do this. X over y, now if your transfer function is this, what does it mean? You added a zero to the system. Where is that zero? You tell me. What is that zero is? So the pole of this system is -1 here. And the zero of this system is at where? What's the zero of this system? This is the kindergarten, man. Solve this equation. I solved this equation. I got p is equal to -1. Solve this equation. Zero is at where? Guys, at where? S plus 1 is 0. So S is -1. So P is -1. Now what is the 0 is? At where, sir? 0. Because S is 0. So your system has a 0 at the origin that we are showing 0 with this circle and a pole at -1 for this system. So having being said, oh, I cannot delete this. So x over y I'm gonna replace again with I omega plus 1. So next class, what I'm gonna do, I'm gonna plot log of omega square over omega square plus 1, and I'm gonna plot x over y to teach you another system. Clear, everybody? Yes? Huh? So I will stop here because I have problem in the PowerPoint. I cannot go ahead. You see that? So see you next week. Okay?
Thank you.
Thank you. I'm gonna share the files with you. Thank you.